to my lecture today. Today I'm actually gonna walk everyone through another exciting topic. Give me 1 second. I'm actually going to share my lecture slide. Okay. Can you see my slide? Can somebody confirm by talking if you are seeing my lecture slide that's projected?
I can't see it.
I need. Okay, thank you so much.
Oh,
Thank you for
actually, I can
confirming.
see it now. Sorry.
Oh, you can see it now. Okay,
Yep.
thank you. Okay, so once again, I want to welcome you to this topic. But just like the way I always do, I think for you to be able to understand what we want to do today, it's better to have a recap on how how we get ourselves, how we find ourselves doing predictor response variable. Before now, we actually trying to characterize relationship between two variables. One is called dependent, the other one is called independent. We also call them several names. The one we call dependent can also be called response. That's why you are seeing predict the response variable. Okay. And the one we call independent variable can also be called predictor. Okay. Can also be called this. Okay. We can say predictor. We can say independent. Okay. We can even say explanatory. Okay. And well, what do we use to denote that? We use X to denote that. Okay. The one Y we call it response variable or we call it dependent. Okay. Please take notes. Okay. So the idea is just like to study relationship between two variables. We basically want to know what kind of model can we use to characterize relationship between two variables. I started in this class by specifying uh, linear regression model. The very first model we can think of is simple linear regression model. It could be right, it could be wrong. We have a way to investigate whether the linear relationship that we have fitted is right. Because in this course, I'm still going to walk you through non-linear relationship. But let us assume, I'm actually walking you through now how linear relationship work. The linear relationship we actually start from the specification of the linear regression model, which you've already seen. And of course, you're going to estimate parameters in the linear regression model, the one I call beta and the beta 1. And after that, you actually do what I call model evaluation, that we also call regression diagnostics. The regression diagnostic is done, in order for us to investigate whether assumptions or conditions underlying the use of that model actually hold. Of course, I walk you through assumptions of linearity, normality, independence, and constant variance. And I remember what we did yesterday. I walk you through how the total variation around the response variable that we also call dependent can be decomposed into what I call explained variation and unexplained variation. I remember we use data set on kangaroo. We use the width and the length of kangaroo. The width of kangaroo was actually the response variable, and the length of kangaroo was actually the independent uh, variable. So, what is new? What do we want to do today? What we want to do today is predicting the response variable. Before you're going to go into prediction, it means everything is fine, like all conditions hold. You've investigated conditions, like linearity, normality, constant variance, and so on like that. There is an absence of unusual observation like outlier, high leverage, and the like. Everything working perfectly. Then we can now think of how can we now use the model to make a prediction. So what do we want to predict? We actually want to predict the response variable that we call the dependent variable. Okay, and that's exactly what we want to do today. Okay, you can see statistics is like a story that goes on and on and on. We don't just find ourselves in this topic. Okay, we've been working on some topics that are actually related. Okay, now I want to walk you now. Now, don't forget, I told you the time in scientific world, we both okay, so this is part of the predictive goal. We want to make a prediction. Now, today I'm going to show you that we can have a prediction for Y. We can have a prediction for mean. There are two types of prediction as far as statistics is concerned. We talk about having individual prediction. We talk about having mean prediction. The two are not the same. Okay, so I'm also give me 1 second. Okay, thank you so much. Now, and not only that, when I talk about when I walk you through this, okay, we're also going to talk about intervals associated with prediction. Okay, because when you make a prediction, whether individual or average, we have what we call point prediction. Point, okay, and we have interval. Okay, the point prediction, you're probably going to get a single value. A single value could be wrong or right. And how do we tell? Okay, whether the results that we got from this survey reflects the overall view of the population, we need interval. Okay, we need interval because of that. So I'm also going to walk you through that. Okay, so I'm going to use different data set today. This data set is data set on rate my professors. Of course, I told you the other time. Um, we of course, I'm also being rated. If you go to the Google and put my name, you're going to see what students say about me. So not only me, about every other professor as well. Okay, so the student actually rate professors based on so many variables like clarity, quality, and so on like that. And of course, the variable they are on 5-point scale. Okay, one being the worst and five being the best. Now, but for the purpose of fitting simple regression, we only want to, of course, because you can only fit a simple linear regression when you have two variables. Okay, one dependent and one independent. The quality and clarity. And the of instructors that were rated, I think in the one large campus in the Midwest in the United States, there are about I think 366 instructors. So we generated the scatter plot. As you can see, the scatter plot, right? And that is giving you evidence of a straight line, right? Okay. Now, this is a research question. The research question, if I know an instructor clarity rating, okay, what can I say about the instructor overall quality rating? Like if I have information about X, can I say something about Y? I can only say something about Y if there exists relationship between them. Okay. And as you can see, that relationship is more or less like that's a straight line. Okay. Now, like I said, we actually want to do numbering. I want to do labeling. Since we want to predict quality using information on clarity, we're actually going to call clarity S and quality Y. Okay. So after plotting that, of course, I need you to take a look at, give me 1 second, the first one. If a specific professor, okay, when I say specific professor, I'm actually talking about individual. You know, I told you the other time, where we want to talk about prediction, we have individual one and we have the mean one, the average one. Okay. Now, I want you to take a look at this now. If a specific professor clarity rating is 3.5, for instance, okay, is a core rating. Okay, this is for the individual. Then we also want to know one for the average. Take a look at this. What is the expected that we also call mean quality rating for professors? That is no longer an individual. Does that make sense now? Okay, with clarity rating equal to 3.5, you know that two are not the same. The first one is for individual, and the second one is for the average. So, like I said, we got two types of prediction. One is for individual, and one is for average. For the purpose of assignment or exam, okay, you need to be able to identify, what they ask you to do. Okay, if they ask you a question that has to do with individual prediction, and you do average or mean prediction, that would be wrong. Okay. Now, you know, if I have a scatter plot and I basically want, maybe, here they said the clarity is 3.5. Okay, I can make use of my scatter plot. I'm just going to draw 3.5 all the way to touch the line, right? The line of best fit. Then I will be able to know my quality. Or another way to do that, the moment I know my beta naught and my beta 1, right? Of course, you've been actually taught how you can estimate your beta and the beta 1. Okay, all I'm just going to do is to plug in 3.5 to replace X. Okay, so when I do that, okay, now I need you to see the model that I actually specify. For individual one, it will have error in it. The model, the fitted model, will actually contain error for the individual one. Okay, now what about for the average one? Is there any error? There's no error in the average one. But let me tell you, whether there is error or no error, both individual prediction and mean prediction will give the same value. I'm going to say that again. Whether you are talking there's an error or not, okay, the value you're going to get for individual prediction is still going to be the same value you're going to get for the average prediction. But do you know where we have difference? Different exists in their standard error. When different exists in their standard error, then there will be difference in their confidence interval. Does that make sense? But when you want to look at it from the point estimate perspective, they're basically going to be the same. But I'm trying to give you now, trying to show you error is contained in the individual one, and error is not contained in the mean one. Do you know why error is not in the mean one? Error is not in the mean one because we have made that assumption. Expected value of error equal to what? 0. On average, error equal to 0. That's what it means. Okay. I can ask a question like this. Y star is what? Because the Y is an individual. That should be a random variable. Okay. Individual, there's natural differences, right? One individual to other, right? But when you take a look at expectation, that's it mean. That's a known parameter. So that's take notes of that. Now I want to go into point estimate. I want to make use of the model. Okay, I want to show you, how we estimate the individual one and how we estimate the average one. Of course, I know the model for individual one. We actually include error, and the moment I know my beta naught and my beta one, my beta naught is 0.221 and my beta one is 0.952, which is the slope. Okay, all what I'm just need to do is to plug in the values, just 3.5. So when I plug in that, that's what I'm doing now. You see, I'm plugging in 3.5 to replace clarity. I already know my beta naught and my beta one. Okay, then the point estimate for the individual now, okay, the point estimate for the quality is 3.55. Let's now see the one for the average. Okay, so but before I go into the one for the average, how are we going to interpret that? We're actually going to say the estimated quality rating for a specific professor who has a clarity rating equal to 3.5 is 3.55. Now, can you see that interpretation now? Now I'm going to go into to the average one. Of course, to the average one, I'm actually going to use expected value of y given s equal to 3.5 equal beta naught plus 3.5 beta 1. Of course, I'm just going to plug that in. I told you the other time, whether for individual one or for the average one, the point estimate of prediction will be the same. Now, right now, we're also getting 3.55, but I need you to pay attention to this. How do we interpret the point estimate of prediction for individual one, and how do we interpret that of the average one? Even though we got the same value, take a look at the interpretation. And I need you to compare the two interpretations. Take a look at the interpretation for the average one. It said the estimated mean of quality rating for professors who have clarity rating equal to 3.5 is 3.55. Can you cite the difference? Can you now cite the difference in the interpretation? You can see they actually have different interpretation, but don't forget, you get the same point estimate. Is there any question on this? Is there any question? Go ahead. Exactly. That is what I do all the time. So your question is, do we get a practice questions or practice exam before exam? Of course, if one lecture will be dedicated for that. Yeah, that's what I do all the time. That's a good question. For those of you online, somebody asks whether I'm actually going to release practice questions or practice exam before the re-exam. Of course, my answer is yes. That is what I've been doing forever. Okay, now I want to go. So when S star is 3.5, I have information about 3.5. I mean, about X, which is clarity. Okay. Now here, I just want to discuss what is the difference between the the formula that I'm actually going to use for individual and the one I'm going to use for the average. Of course, for the individual, I told you there's gonna be error in these. For the average, there's no error. Okay, but their estimator will be the same. What do we mean by estimator? Estimator is a formula or a method that we use in estimation. Do you know why we actually got the same result for the two? We got the same result because we use the same estimator. The same estimator will lead to the same result. That's exactly what you're seeing now. Okay, now I've walked you through how to get the point estimate of a prediction. But let me tell you, we cannot rely on the point estimate of prediction because you know why? Because they could be wrong or right according to the classical approach of probability. And that is the reason why, if we want to rely on our estimates, we need an interval. We need to describe this estimate in an interval. Describing estimates in an interval is incorporating what I call the margin of error. And the margin of error is going to go, you're going to consider error to the left and the error to the right. Now, because of that, we're going to have a two-sided format of the confidence interval, which is basically going to be point estimate plus or minus. When you take a look at the distribution multiplier and the estimated standard error, when you multiply them, we call them margin of error. What do we call margin of error? The margin of error will enable us to know how reliable is our estimate. Okay, if I want to know how reliable. Okay, so because of that, I need you to recall what you've done before now. Where you normally hear about confidence interval for mean. You've done that in a lower course. Oh, the confidence interval for mean, 95% confidence interval, 90% confidence interval. Because if you want to describe something in an interval, you need to be able to disclose your level of confidence. Okay, what do we mean by level of confidence? The level of confidence and the level of significance are mutually exclusive. If the level of significance is 5%, the level of confidence is 95%. That's what we mean. Okay. So what that means is, if I have 100 intervals, if I have 100 intervals, the true values of the true value of the parameter will lies in 95 out of 100. 95 out of 100 intervals, that is what we mean by 95% confidence interval. Okay, so now take a look at this now. I want to remind you of what you've done before. What you've done before, you make use of this formula, right? Based on what you've done before, the confidence interval for mean. Why, mean, it's a point estimate, a single value that could be wrong or right. In order for us to be at a safer side in research, we need an interval. We need an interval estimation. Okay, so of course, the x that you are seeing there is the standard deviation divided by the square root of sample size. So the whole thing, standard deviation divided by the square root of n, is what we call the standard error. Then the quantifier, we're going to check that either from a normal distribution table or from a T. Do you remember our first class when I actually reviewed basic statistics? I think I walk you through two important distribution, normal and T distribution. The idea of that is basically going to be used in figuring out the quantifier. Okay, now I want to start my confidence interval. I basically want to start that with that of the average. Now, let me tell you this. When I'm talking about interval for prediction, when you see me, if I mention confidence interval, I'm actually referring to interval for the average. But if I mention prediction interval, I'm talking about interval for the individual. I'm going to say that again. When I mention here confidence interval, I'm basically referring to the interval for the average. But if I mention prediction interval, if I mention prediction, okay, prediction interval, okay, then I'm basically referring to the interval for individual prediction. Does that make sense? Now, I want to start now. I said confidence interval for that. Okay, I'm actually referring to the mean prediction, expected value of y given that. Okay, the whole thing is basically going to start from the point estimate, right? And the point estimate is going to be that, of course. Before you can obtain your point estimate, you basically need your beta naught curve, the beta 1 curve, and of course, you need to know the values of the x for you to be able to predict, right? Okay, so now after finding that, now we need to identify the distribution of the difference between what we predict and what happened in reality. You know what I'm trying to do now? I'm actually trying to derive what is basically, because I need a standard error. Then the only way to get to standard error is to get the variance. When I get the variance of the difference, I'm going to find the square root of the variance, and that will give me the standard error. Why do I need standard error? I need standard error when I want to construct confidence interval. I'm going to say that again. Standard error is needed when constructing confidence interval. Not only confidence interval, even by the time we're going to start hypothesis testing, because we're still going to test hypotheses about parameters, about regression parameter, we need standard error as well. So what we now is that the difference between predicted and the expected value of y given s follow normal distribution, okay, where the mean of the difference is going to be 0, and the variance of that difference is sigma squared into 1 over n plus x star minus x bar all squared divided by xxx. Now, you know what I'm going to do now? If I want to set it up, finally, I'm actually going to have two different scenarios, and I need you to pay attention now. If you take a look at the sigma squared, right? The sigma squared is variance, but sigma is the standard deviation. We call that population variance, and sigma is population standard deviation. Now, in statistical analysis, if the population standard deviation is unknown, we're actually going to check from T table. We're going to use T distribution multiplier. But if the population standard deviation is known, we're basically going to be checking from normal table, the Z table. Has anybody heard about Z table? Okay, so please pay attention. Now, if you take a look at the two, the formula is the same, except that one is sigma cap, the other one is sigma. Can you see the difference in the formula? What you have, you know, I'm talking about the purple one, the last formula, 2, is the same, right? But the difference is just a sigma cap, they are a sigma in the other end. Okay, when the population standard deviation is not given, it means we need to estimate the sigma, which is going to be sample standard deviation. The sample standard deviation is sigma cap. The sigma without a cap is a population standard deviation, which means you have been given that one, and that is why it is no. Please pay attention to that. Okay, now I just discussed what is the way from this slide. The takeaway from this slide is, if I want to construct an interval for the mean prediction, I actually need a standard error and a multiplier, because the combination of the standard error and the multiplier will actually give you the margin of error. That the margin of error that you're actually going to subtract from the point estimate, and you're also going to add the margin of error to the point estimate, and you're basically going to have two values, right? The lower end point and the upper end point. What I just showed you now is the standard error for situation where we're focusing on the average prediction. But what about individual prediction? I told you, for individual prediction, we're going to call it prediction interval. Look at the word prediction interval. It means I'm focusing on individual prediction. I want to construct interval for individual prediction. We'll call it that. Now, let's see the difference between the two. Oh my God, I need you. Oh, give me 1 second. I actually need you to, what is the difference between this and the one that I showed before? Here, you can see in the square root, there is 1 plus, right? I'm going to go back. I need you to look at the standard, the standard error, the last one. Okay, look at that and this guy. Do you see that? Is there any in the square root? Do you see 1 plus? No, that is the difference, right? Okay, so now, because I'm actually going to show you, I'm not going to write everything in one page now. Oh my God, take a look at this now. If you look at the individual one, okay, you can see the individual one is the last one, and the mean one is the second one. Can you see the difference? Look at the difference between the two. Okay, they're going to have the same point estimate, right? But the difference is just what you have in the square root. In the square root of for the individual one, there is 1 plus. Okay, and what you can see now, there is a difference between the two standard error. If there's a difference between the two standard error, then when you construct interval for individual prediction and for the average prediction, one will have a wider interval. Why is it that one is going to have a wider interval? Because the fact remains their standard error is not the same. Does that make sense? Okay, so that is what I'm just trying to show you now. Okay, where anytime you see CI, confidence interval, the confidence interval is for the mean, is the interval for the mean prediction. While PI, prediction interval, will be the interval for the individual one. Okay, now we want to go back to the exercise. We're still talking about Professor John Clarity rating. The other time, the Professor John's Clarity rating, okay, was actually 3.5 and provide a 95% interval for its quality rating. This, because we're referring to one professor, it's going to be an individual one. Please make sure you pay attention to the formula you're going to use. Okay, we're referring to Professor John. That's an individual, not professors. Now, do you see the standard error that I'm using now? Can you see the standard error now? It is the one that have 1 plus. You see that, right? Okay, now, so like I said, for individual one, it means we're interested in prediction interval. Okay, now when we need to first get a point estimate, right? Okay, you plug in, you've done that. Then we now need the margin of error. If you want to get the margin of error, you need to first get a quantifier. if they say 95%, where do I get the 0.975 quantile from? I'm going to show you now. I need everyone to pay attention now so that you'll be able to see how I got that. Statistics is very, very easy. Okay, statistics is very, very easy. Okay, so if the confidence interval is 95%, because 95% interval, the 95% interval will mean the alpha is going to be 5%. Okay, the alpha is a level of significance. That is a level of error. That is the numbers of times out of 100 we can mislead. If you can mislead 5 times out of 100, then you are 95% confident. Okay, so you're gonna do alpha over 2 because we're talking about 2 tail, which this guy is 0.05, so it's gonna be 0.05 divided by 2. Then you're gonna do 1 minus alpha over 2 minus 0.05 divided by 2. That will give you 0.975. Okay, and that was why you're saying 0.975. If I want to get it from it's basically that is a code. The code in getting the quantile, okay, the code in getting the quantile is quantile. Okay, 1 minus alpha over 2, 1 minus alpha over 2, that this guy here, right? The degree of freedom is n minus 2. Do you remember yesterday? That was the degree of freedom for the error. You're actually going to use the degree of freedom for the error, n minus 2. Okay, so R will automatically be 197. Okay, now all we just need to will actually information about what sigma, right? Please I need to pay attention. What we need to know about sigma car, and of course the n is the numbers of professors. We're told it's 366. Okay, then we need information. The S star is 3.5. X bar, that is the mean of clarity. Then the SSS, I told you the other time, the SSS is variation around X. X, summation X minus X bar squared. Now, what you're going to do, you can go to R, run a linear regression in R. When you run a linear regression in R, that is the code. MOD equal LM quality on clarity, your data equal to rate prof. Then you have all of that. Now, if you want to get the mean, the X bar that we talk about, do you see that in the rectangular? Mean into rate prof $ clarity, that gives 3.5, right? Then you need sigma, right? The sigma, in the formula, if you take a look at the formula, there's a sigma curve, right? Where where can you actually get that sigma from? That is a residual standard error in the output. Can somebody see residual standard error in the output right here for this line? That's a sigma curve, 0.1828, and that was why I actually said sigma curve equal to that. Do you see that now? Then what's your n? 366. Okay, how am I going to know n? If you look at the degree of freedom in the table, 364, right? And don't forget, to get degree of freedom is n minus 2, right? Okay, if n minus 2 is 364, what is n? Now n will be 366. Okay, so you have information about all of that. Then we're going to plug it in. Okay, and of course, by the time you do that, you actually go get your result. Okay, it's going to be in the interval. You're going to have the lower endpoint and the upper endpoint at the end of the day. Okay, so this is a plot. Okay, but that's what I want to show here. This is what you're going to get. When you do the confidence interval, the one for average, you're actually going to get 3.53 to 3.57. For individual, it's going to be 3.19 to 3.19 to 3.91. Which one has a wider range? Which one out of the two? Is it the average one or the individual one? Can somebody tell me? Which one has a wider range? The individual one. And what does wider range implies? Because the wider range is trying to tell you the larger value of the standard error. Then let me tell you this. The wide in statistical analysis, when I'm comparing two intervals, I'm basically going to go for the narrow one. And that is why the one that is narrow is the average one. And that is why in statistics, we normally focus on average. We don't talk about just individual prediction. We talk about average prediction. You know why? Because the interval for the average is very, very narrow. Narrow because the standard error associated with that is very small. When the standard error is small, the margin of the error will be smaller. When the margin of error is small, then the interval is going to be narrow. So what makes an interval to be wider is when the standard error is large. Does that make sense to everyone now? Now, I prepare a code here. Okay, this my TA is going to walk you through this code in the lab tomorrow. On Friday. Okay, predicting response arrow codes. Okay, I put it right here for you. Okay, so like I said, my TA is going to walk you through all of this. How do we do that now? Okay, the code that I've provided here. Okay, so my TA is going to walk you through all of that. So I'm going to say, this is going to be the end of my lecture today. I'm going to have a summary of what we today. The summary what we have done today is just we focus on prediction, predicting the response. Of course, you know, in the scientific world, in the stochastic world that we live in, we actually want to understand the world. We want to explain the world, and we also want to predict what is going to happen next. Okay, and of course, the focus today is having an established relationship between variables, you know, by way of investigating whether assumption hold. Of course, the next thing we can do is to now begin to make prediction. And there are two types of prediction. We have individual one and we have the average one. So whether individual one or average one, we have point estimate, we have interval estimate, which I walk you through today. The point estimates for individual prediction and for average prediction is the same, but the interval is not. Why is it that interval is not? Because the standard error associated with, you know, with the point prediction is larger than the standard error associated with that of the mean. And that is the reason why when you look at the intervals, the one for the average will be narrower. Like the interval will be small, narrow, very narrow. But the one for the individual will be very wide. And that's actually justify why we normally use average in statistics. Because the result based on average is reasonable because of the fact that the standard error is very small. And that is exactly what I've demonstrated today. Okay, so let me just prepare your mind about what we're going to do. You know, time, prepare your mind. So what we're going to do Okay, what we're doing tomorrow is what of if assumptions are violated? What am I going to do? I've specified linear regression to model relationship between two variables. The two variables may be amount spent on advertising and the volume of sales. It could be how does age relate to the length of stay in hospital. It could be the percentage of votes received by a particular political party in 2016 and 2020. It could be any of that. And of course, when we specify linear regression model, the fact that we've specified a model does not mean that very model will do a great job. We have a way in statistics to investigate whether a model is going to do a great job. And the way we're going to investigate that is to revisit assumptions. Okay? We investigate whether assumptions of linearity hold, assumptions of normality, assumptions of constant variance, assumptions of independence, and the what I call the absence of unusual observations, whether outlier or high leverage. It is only when all these assumptions hold that we can use our model to make a prediction. But what if there's a violation of assumption? What are we going to do? What we're going to do, we are not going to rush to predict, because when we rush to predict, whatever recommendation from that model will mislead. Now, if there's a violation of assumption, what are we going to do? What we're going to do is what we call transformation, which is what we want to do tomorrow. It means we need to transform our model. Instead of us to be talking about linear, we're not going to be talking about linear anymore. We're going to generalize our linear model. Okay, we're going to be, we're actually going to be thinking in direction of whether we're going to fit linear regression on a logarithmic scale, on an exponential scale, and so on like that. So tomorrow's topic is an intervention. We normally go there whenever there's a violation of assumption. You can now see that statistics is more or less like a story. That is what I have for you tomorrow that I call variable transformation. Is there any question before I go today? Is there any question, whether in person or online? Is there any question before I go today? Yeah, go ahead. Oh, that is not meant for you. Sorry about that. That was what I put a passcode. I apart from being a professor, here I'm also in the summer I'm in charge of consulting research for the undergraduate. So those meetings are for researchers that I want to meet tomorrow. Okay. You don't have to. Oh my God. You don't have to. Thanks for asking that question. Okay, make sure you all stay safe and see you tomorrow. Bye for now, everyone.